We're working on Advent of Code, day 14. We're actually 20 minutes away from day 15's problem landing, but I'm running a little bit behind schedule. So we're going to try to work on day 14 right now, and if I'm feeling up for it, we can go straight into day 15 once I'm done. Let's get started. Okay, so the problem for day 14 is called extended polymerization. It's funny, I was just thinking about seasoning a cast iron pan, and that involves polymerizing oil onto the surface of the pan. And what a coincidence that today's problem is about that. The incredible pressures at this depth are starting to put a strain on your submarine. The submarine has polymerization equipment that would produce suitable materials to reinforce the submarine, and the nearby volcanically active caves should even have necessary input elements in sufficient quantities. The submarine manual contains instructions for finding the optimal polymer formula. Specifically, it offers a polymer template and a list of pair insertion rules, your puzzle input. You just need to work out what polymer would result after repeating the pair insertion process a few times. For example, it starts with NNCB, and it's got a bunch of, input to output rules. The first line is the polymer template. This is the starting point of the process. The following section defines the pair insertion rules. A rule like AB to C means that when elements A and B are immediately adjacent, element C should be inserted between them. These insertions all happen simultaneously. So, starting with the polymer template NNCB, the first step simultaneously considers all three pairs. The first pair, NN, matches the rule NN to C, so element C is inserted between the first N and the second N. The second pair, NC, matches the rule NC to B, so the element B is inserted between the N and the C. The third pair, CB, matches the rule CB to H, so element H is inserted between the C and the B. Note that these pairs overlap. The second element of one pair is the first element of the next pair. Also, because all pairs are considered simultaneously, inserted elements are not considered to be part of a pair until the next step. After the first step of this process, the polymer becomes blah, 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 blah. Here are the results of a few steps using the above rules. The polymer grows quickly. After step 5, it has length 97. After step 10, it has length 3073, so on and so forth. Taking the quantity of the most common element B and subtracting the quantity of the least common element H produces 1749 minus 161 equals 1588. Apply 10 steps of pair insertion to the polymer template and find the most and least common elements of the result. What do you get if you take the quantity of the most common element and subtract the quantity of the least common element? To begin, get your puzzle input. Okay, so I think this problem, well, I don't know what to think about this problem yet. I guess I'll know a little bit more when I actually start to do it. I have some inkling of how I want to do at least my first implementation. The question I have is, does every possible pair of letters that appear here have a rule for inserting things? And this matters just because I want to know if essentially we're always growing the size of our list of polymers or elements. Is our list of elements always growing at a consistent rate? Which is to say, are you always adding, if you have n elements in the list, are you always adding n minus 1 elements? And that would be true as long as every single pair of possible elements is represented in this list. So we have, it looks like we have a B, an N, an H, a C, and that's it. And the number of times you can order those two things together is 4 times 4 is 16. And I think 4, 8. I'm counting, what is this, 4. That's the 8th one. That's the 12th. Okay, there's 16. So I think we are representing all pairs. So essentially we are going to be growing this by n minus 1 units every single time, or elements every single time. Okay, so let's go ahead and try to get started here. Oh, geez, we have a lot more letters here. Okay, so the first thing we want to do is just get our template, and then, I have the wrong day open here. What I want is main.rs for 14a, Close the directory. I should really be opening it. Here we go. All right, that's nice and clean. Okay, I'm just going to open the input just to have it on hand. And let's bump up the font size to make it a little bit easier to see on the video. And let's get on our way. So the first thing we want to do is just read in the first line, which is going to give us the template. So the input is there. Let's get an input iterator. Let's just call it lines. And that's going to be mutable because we're going to be actually be iterating over the iterator. So we're going to be mutating it. So our template is just the first line. And then we are going to consume blank line. Here. And then we're going to read in what are we calling these? Are they rules? Pair insertion rules, right? So our insertion rules are going to be a pair of characters followed by the rule that followed by the one that we create. So maybe I'll just call this a tuple of 3 things. Is that a little bit too weird? So our rules are going to be a vector of 3 characters basically. And we're going to map this. Line is a string. We are going to split the string by this delimiter. And then let's just say that the first 2 characters. What's the way that I really want to do this? I really wish I just had scanf, but we don't really have it. I could do regular expression on these. Gosh, regular expressions are so cumbersome. I'm always so reluctant to use them. I could just address these characters by their index, really. I don't need to be so laborious about this. Because we know that the first character of each line is going to be our first element. The second one's going to be our second input element, and then the 1, 2, 3, 4, 5th element of that line is going to be the output element, right? So if we actually just make the string into a collection of characters, or if we can get a character at a particular thing, is there anything in Rust that will give me that? Is it get? Returns a subslice of string. Why don't I Google this? Rust. Get nth character of string. It's probably going to have me collect this into a vector, but let's see. I could do chars.nth. Although that updates an iterator, I'm assuming. It's cumbersome, but I'm just going to go ahead and do it. The parsing is not going to be that performance sensitive. Let in A equals line.chars.nth. It's the first one. Let's unwrap that. Let in B. It's the first character, and let out equal to, what did I say, the 5th character? 0, 1, 2, 3, 4, 5. It's actually the 6th character, right? Because that's 4 characters there, and that's 3. So it's 7 total. It's the 7th character, but it's index 6. And yeah, we're just going to return in A, in B, and out. And then we want to collect over this. All right, let's go ahead and print our rules and see what we get. Let's also print the template. How'd you get snuck in there? All right, let's run that bad boy. CHO is our last one. It looks right. Our first one is OP and H. Okay, great. So what I'm thinking now is that we're probably going to want to be looking these things up in a kind of like hash table, right? So even this vector that I've kind of created here may not even be the thing that I really want. What I want is kind of like a hash table that takes the input, the two input elements in a sequence and then returns the output element. So maybe it'll be something like this. Let mute rules is a hash map whose key is 2 characters and whose value is a single character, right? And instead, I'm just going to iterate over these lines. And we're going to do a similar thing here where we just pull the characters out. But then we're going to insert into the rules the input tuple and the output as the value, right? Let's try that instead. KP goes to H. The ordering here is going to be kind of random seeming because a hash map is not ordered strictly. But if I look for KP, it indeed goes to H. And if I look for P and K, that should be in here, right? PK goes to K. So let's look for that. P, K, PK goes to K, right there. Okay, so it looks like we've got a nice sort of lookup table now. Okay, so we're supposed to run 10 iterations of creating, 10 iterations of applying the insertion rules, right? So let's call the template. I think what I actually want to turn this into is I want to turn it into the current state. Let's just call it state. Got that first line. We're going to convert it into characters, and then we're going to collect it into a vector of characters, right? Okay, now we're going to loop 4 times, or 10 times, rather. Let's read the rules one more time and just make sure that that's what the right number. Apply 10 steps. Okay, great. So I'm going to call this let next state equal to a vector of, I guess I'm just going to use the 0 character, and we're going to have our current state, its length. We're basically going to double it, but we're going to -1 because essentially we're just going to have one new character in between each of the previous characters, right? So now we're going to iterate over each character for I in 0 to state.len -1. We're gonna be looking at each pair of characters. So I want to stop before I get to the very last element. So the first thing that we're going to do is we're going to copy next. We're going to copy the current character I. It's going to be 2 times I equals state I. Two times I state plus 2 times I plus 1. We are going to look up in our hash table what this next character will be. So it would be rules of state I plus 1. I think I needed to call get here, actually. Get this tuple. Probably need to get it by reference. And it's going to ask me to unwrap here, I'm guessing. Yep, it's an option. I want to unwrap here, and I want to dereference at the end of that. Finally, 2 times I plus 2 equals state I plus 1. So I think the math here actually needs to be, is that 3 times I? Is that correct? It's going to be very easy to be off by 1 here. I'm having issues connecting to my iPad, which is totally fine. Sidecar has been super flaky for me for whatever reason, and I've had to restart my computer a bunch of times. So hopefully I'll still be able to hear folks in chat if they do happen to arrive. I didn't advertise on Reddit tonight because I realized I was spamming the Watch People Code channel, or rather this Watch People Code subreddit, without even realizing it. There's not a lot of foot traffic there, and so I was posting one message a day, and I ended up being the consecutive poster a few times. So I'm going to chill out on that. At any rate, back to the problem. We just want to make sure we're not off by 1 here, writing into this next state variable. And by the way, I'm just going to be overriding state with next state. So let's go ahead and try to figure this one out. Let's actually just take a look at our input here. In a scratch buffer, we are going to have K and then some value and then B. And then some value and then K. So B is basically going to be at 2 times its original position. So I think what I'm actually missing here, or what I'm doing incorrectly here, is I shouldn't be writing the second one, because it'll get written on the next loop over. But what I do need to do is make sure that next state, that its last value, 2 times state.length minus 1, and this is going to be in parentheses, is equal to state.len minus 1. And let's actually maybe just put this into a variable. Let prev last equals state.length minus 1. Make that prev last. Make this prev last. And that should be a little bit clearer. So after this point, we are going to want to count. We're going to want to count the number of letters that we have. You know, I'm realizing now that I think I can actually sort of maintain the count in a hash map up here. So if I just say let mute counts, which is a hash map between a character and a usize, which is the count. we want to seed it by iterating over the current state. So for C in state.iter, we are going to insert into counts or add to it, right? So counts.entry using C, we're going to modify it, so we're going to get some count val plus 1, or we're going to insert the value 1 because we start with 1. Dereferencing that. Dereferencing this. And modify. Oh, I see. Modification. We're just modifying the actual pointer to the value there. So I think it's star plus equals 1. Yeah. And then each time we create a new character, we just add to the count there. So we'll do a similar thing here. So let's actually store the new character in a variable. Let new element equal this. And then we'll do the same thing that we did up there. This time we're going to use new element as the key. Okay, so now that we've got that, we need to find the most frequent and the least frequent of these. So let's see. How do we get that out of the hash map? Counts.iter. We're iterating over the key and value pairs. Can we do... I guess we can do min by. And we really just care about the values, don't we? Let's unwrap both of these because we know that they're going to be in there, and then we're just going to print the difference. So we're flying pretty blind here. Okay, I'm missing a semicolon there, and hopefully that takes care of all our errors. We're flying pretty blind here because I'm not actually printing out the state, but we're just going to go for it. Oops. Pressing too many keys at the same time. 2,435. I'm glad it did an infinite loop. That's always a huge relief. Okay, so it looks like we got it right. I almost always don't believe my luck when I get it right the first time, but I think the last few problems have had some reasonable luck with that. So hopefully this means that we've just interpreted the problem correctly. Let's go ahead and go to part 2. The resulting polymer isn't nearly strong enough to reinforce the submarine. You'll need to run it more steps of the pair insertion process. A total of 40 steps should do it. In the above example, the most common element is B, occurring, billions of times. Apply 40 steps of pair insertion to the Polymer template and find the most and least common elements as the result. What do you get when you take the quantity? So it's the same mathematical formula. We're just changing the number of iterations to 40. So what's going to be a little bit crazy about this is we're going to essentially double the size of our state array. We're going to be doubling the size of the state array 40 times, right? So is that 2 to the 40th? And I don't know. I think we'll run out of memory before we get there, right? Let's actually just change this even to 20 and see if we can we can finish running it. Yeah, even when we go to 20, you can see that this program is just taking forever to run, right? And I can try to make a release build, which should run faster. So 20 actually made it. I'm guessing that this is going to be many orders of magnitude slower. So I don't know if we're going to be able to get to 40 before we crash my computer. Because if 30 is taking that long, 40 is certainly going to take forever. So now we're running into, I think, what might be the first really hard problem of Advent of Code this year, which is not to say you should feel bad if you felt like other problems are really hard. It's just for me, usually I just consider problems really hard if I just don't have any intuition of how to crack them right away. And so far this year, I've been lucky and I've had at least some hint of how to approach some of these problems. This one's a little bit scarier to me because I think what it's going to involve is some amount of problem analysis, right? So what I mean by that is like we're going to have to come up with some sort of way of analyzing the growth of our state so that we can kind of project into the future or 40 iterations into this what our state will look like. And that's either going to mean that when this grows, it's going to have some kind of predictable pattern, or we can actually observe step over step that there's essentially some kind of deterministic formula where we can calculate how quickly each one of these letters is increasing step over step. This is day 14. I am running late, so I haven't gotten to today's problem. So yeah, I'm just working on day 14 right now. I lost the chat history, but Shurshak, if you're still on, yes, I'm working on day 14. And I've run into the hard problem of part 2 already. So we'll see how long it takes for me to sort of complete my analysis here. Maybe there's a way where we can, rather than just generate the entire state, we can just know how many of these pairs appear, right? We can just keep track of the number of consecutive pairs. And in that data representation, you're just going to have a list of there's 102 here, so there's like 100. So that means that that means there's 10 letters, right? You're just going to have 100. You're going to store 100 of these pairs, and yeah, for every one of those two, you can basically, if you basically say, okay, well, I've got NK, for example. I know that what the result of that is going to be an NS and an SK. So what I'll do is I'll subtract one NK from my total, but I'll add one NS and one SK. And then I can just multiply, right? So I think that seems like the way to do this particular problem, right? So our counts will be, I think, pairwise counts, right? Or maybe we'll have a separate counts. We'll have let mute pair counts, and that's going to be a hash map of 2 consecutive things plus a usize. And to build this up, I'm just going to iterate through my current state. So that's going to be state.length minus 1. And we're going to just add 1 for every pair, right? So it's going to be a similar pattern to what we had above here. So our pair counts is here, and our pair is going to be state I and state I plus 1, right? And in this case, I think we don't really care about the state anymore, or we're not going to try to update the state that we were doing it before. Instead, what we're going to do is iterate over our pair counts. And what I really want to iterate over is the keys. And I'm just trying to figure out how can I make an iterator for this that will also allow me to mutate. Also let me to mutate the hash map at the same time. This pattern of sort of like iterating over keys or values of a hash map and then modifying the hash map within the iteration is a pattern in Rust that I haven't quite figured out the best form factor for. So just got a chat message. SureStack says you can't do it. Yeah, so thanks for confirming that. I think what I will probably do in that case is just pull out the keys of the hash map and clone it into a vector, and then iterate over that clone. That's I think what I'm going to try to do. I feel like Rust should have some kind of convention for doing this, or essentially, or maybe I'm just like thinking of it the wrong way. Yeah. Thanks, SureStack. Yeah, keys, clone, and then iterate. That seems like maybe what it is I just have the wrong paradigm in my head when I'm writing Rust. But that type of problem, that type of pattern that I'm talking about, is essentially the first tool that I would reach for using basically any other language, right? Iterate over the keys of something and then modify. If you're iterating adding, it might result in iterator invalidation. Yeah, that's totally correct. In this case, I'm not going to be changing the number of entries in the hash map. So iterator invalidation, I think, maybe not possible in this particular type of problem. But since I'm also not changing the cardinality of the hash map, maybe cloning is fine too, right? It's not like I'm scaling the problem up by iteration. So let's just go ahead and I can actually just create our pairs, just a list of pairs outside of the loop because it's static, right? Or it's not going to be static because the way that I created this pair count is from the initial state of the problem. What I should probably do is actually create the pair count from the rules, and this way I can initialize the hash map to 0. And then I'll have an entry in there for everything. I mean, really, I can probably just like let mute pairs, which is a vector of char, just build that up. And then the pair counts I can also build up from here. And yeah, let's just get this shot. Our pairs, we're going to add in A, in B, and then our pair counts, we're just going to insert. I should probably just stick this in a temporary, but I think it's relatively clear what this means. We're going to insert a 0 value here for each one of these. Alrighty. So now what we're going to do is we can get rid of this or insert in here. And we should have a fair amount of confidence that this is going to just we're always going to hit this closure in here because the pair should exist inside the pair counts hash map. It is complaining about the lack of a semicolon. Now, I have these two loops sequentially here. What I think I might do, well, this is fine. I'm not gonna fuss too much about this. Oh shoot! You know, I realize I am overriding my original problem, which is, I think, something I do a lot. So that's fine, though. I actually think that what I'm going to try to do is reproduce the answer to part 1 using this new algorithm. And because if you think about it, part 1 and part 2 are essentially the same problem, except the iteration range is different. So if I can reproduce the answer to part 1, I'll have confidence that like my solution for part 2 will be good. Okay, so let's make sure that state isn't mutable anymore, because I don't want to like essentially create this solution where I materialize the entire list of elements every iteration. That's what we're trying to avoid this time. What we are doing instead is, for each one of these iterations, we're going to iterate over the pair counts, or each one of the pairs. So for pair in, or really we can do, let's do in A, in B, in pair count pairs, in pairs, dot iter. What we will do here is apply the rule for this pair. And the result of that rule is going to be here. Let new element equals this. And we are going to update pair counts this is some value. So because we are now separating two items in a pair that used to be consecutive, we need to subtract one pair from those two, but then add a new pair for the original first element and the element that we just created, and then the pair that contains the element that we just created and the second element in the original pair. This is a plus. And then we do new element in B. Okay, and in this case, we also want to update our counts, which is happening here for the new element. And then what is it complaining about here? Is this, I need to borrow here, or rather dereference, because these are pointers because of the iteration. Same thing here, and same thing here. So all the rest of this stuff is old code. It's yesterday's news. And I think that maybe should do it. There's a lot of code, a lot of typing here. So I'm hoping that aside from these like compile errors, that this covers all of our logic here. Got to add some more dereferences here. And that does it. Let's try running it. Okay, cool. Attempt to subtract the overflow. So I'm assuming that's this line with subtraction. And the pair counts is, I did declare it as a U size over here. So I think the overflow is it's saying that I'm trying to subtract -1. Oh, I see it. I think what I need to do is make sure that the pair count is at least 1 before I continue with the rest of this stuff. Oh, and I think what I'm not doing is multiplying, right? I need to multiply by the count, right? So let pair count equal to pair counts dot get of our pair, which I think is going to be this awkward construction here. And we're pretty sure it's going to be in there, but it's going to be potentially 0. So if the pair count is less than 1, we want to continue. We want to go on to the next pair for this iteration. Let's dereference up here. I just want a usize. It's fine. And then we are actually going to subtract pair count here, right? Because this is the number of times that we're applying the rule. Oh, no, wait. This is definitely just, yeah, this is plus pair count, because this is the number of times we're applying the rule. And all of these ones are also pair count. And this one is also pair count. Okay, let's try running that. Oh, that's massive. So I think I probably did not do this correctly. What was my original answer was 2,435, right? So I definitely I was not able to reproduce the original result, which is fine. But yeah, let's just think about it. Why don't I print out the pair counts before I get any further? What are the pair counts from the original input? So I've got one HN, which looks to be true. I've got one BK. Doesn't look like I have another BK. Do I have any in here that are actually, that should be 2? I think these are all 1s, right? It doesn't look like I have any that should be 2. Let's take a look at the second iteration. Let's actually just iterate once. And then we'll go ahead and print pair counts one more time. Why don't we, oh, I don't have the, I'm not materializing the state anymore, so I can't print that out. I technically don't need counts if I know pair counts, because I can derive counts from pair counts. So what I'm doing here with counts is really just an optimization. All right, so this is actually a really big input. It may be worthwhile for me to run this on the test input, just to make sure that I'm doing this correctly. After the first step of this process, the polymer becomes NCNBCHB. So I'm running this just one step, and hopefully I can derive this from my outputs here. Oh gosh, yeah, so I shouldn't have 9 Bs just running this once, right? I only ran this once, and somehow I was able to get myself into a state where I had 9 Bs, even though the result really should only have, what, 2 Bs here? So my original pair counts when I started first thing I've got is a CB, which is correct. And I should have an NN, which is correct. I should have an NC. Yep. And then a CB, which I verified above. So after the first iteration, I've got way too many in here, right? I should really only have, if I had 4 characters the first iteration, I should have 7 characters total the second iteration. Right. Let's go ahead and print the pair while we're at it. Let's print the pair that we actually handle during the first iteration. Ah, interesting. Am I iterating more than once? Because when I'm printing these pairs, there's a lot of pairs that are coming in through here that have a pair count greater than or equal to 1, which is a little bit mystifying to me because we just printed out the result of this. And so, for example, CB, I get why we're seeing it because CB does have a value of 1 in here. But for example, HB, if I pass that into pair counts as a key, HB should be 0, and the result of this fetch here should be 0, and which should just march us right past this step in the iteration. So let's actually just print both the pair and the pair count and see what it's actually telling me. CB has a pair count of 1. HC has a pair count of 1. Is that reasonable? Am I simply just running this too many times? 0 to 1. I mean, really should just be running this once, right? Oh, I see what's happening. I am modifying pair counts in subsequent iterations here, but what I really want to do is actually create a new pair counts, because what I'm violating is this rule that they described in the description. They described here where they said, also all pairs are considered simultaneously. Inserted elements are not considered to be part of a pair until the next step. Okay, so I think essentially what I need to do is create a new pair count right here. Let next pair count hash map. What I really want to do is actually just clone pair counts. Clone. That shouldn't be too expensive. Then we modify next pair counts here. And after we've done iterating through all the pairs, we set pair counts equal to next pair counts. Let's go ahead and restore our original input, print it out, see if we get the original answer. 6. Oh, I'm only iterating once. We want to go to 10. 2,435, that sort of rings a bell. 2,435. Okay, so I think our implementation here, it looks pretty good. So let's get rid of our debugging output. Still missed one. Here we go. Just got 2,435. Fantastic. So let's be a good citizen and commit that to Git. Let's finish that up. And let's copy this into a 14b directory. And now that we've got 14b, we are just going to crank a number up to from 10 to 40. And that's some really massive number here. We're just going to plug it in and cross our fingers. Whew. Well, we got that right. Which is great. I feel fortunate that I didn't have to sort of tread too much water trying to come up with a solution here. Luckily, just a different data representation rather than just materializing this sequence of characters. We can just think of it in terms of just pairs of sequential characters and the number of times those sequences appear. I guess what we're really saying is that as far as the rules are concerned, we don't really care what order that OV, each pair has relative to other pairs. Like, we don't really care that an OV appears in front of an FN or behind an FN. We just care that O comes before V. Right. I think that's the insight for this problem.